Maths educational video. An application of polar coordinates in double integration. When the region of integration is one of this kind, bounded between two polar curves, upper bound is r equals to h theta, a function of theta, and the lower bound is another function g, between two values of theta, alpha and beta. Graphically, these are lines through the origin as shown. Then the double integral has a special formula, as shown in the box. A special case emerges when the lower bound is identically 0. So it's a zero function, which means you are at the origin. The region looks like this. This case is important because any sector of a circle, including a circle itself, will belong to this kind. When given a new formula, the natural question to ask is, why would you need such a formula? We recall in the rectangular setting, these are formulas we already know. If a region is of type 1, the double integral is given by this formula. If it's of type 2, we have a corresponding formula for the double integral. Obviously, one reason for using these polar coordinates is that the region given is neither of type 1 nor type 2. Like the one shown here. It's not hard to tell. This is neither of type 1 nor of type 2. So this gives us a way to deal with double integral when we have a region of the third kind. Let me give you an example where the use of polar coordinates will be more convenient. Here we are asked to evaluate a double integral for some function f when the domain is a quadrant of a circle. As you can see from the diagram, a circle has Cartesian equation y equals to the square root of 1 minus x squared. But in polar form is r equals to 1. So immediately you can see the advantage. Instead of dealing with square root of a quadratic function, you are just dealing with a constant term. So that's actually one reason why the use of polar coordinates is good. There's actually another reason. Over here, we can actually treat this as a type 1 region, where x lies between 0 and 1, and y lies between 0, the x-axis, and this circle, which is square root of 1 minus x squared. So using the formula we know in Cartesian form, the one in green is what we need to compute. But immediately we have one challenge. It's usually tough to deal with integration when there is a square root of a quadratic term. So it could be done, but it's going to be very tough. But if you use polar coordinates, computations can be much simpler. As you can see here, if you use the polar version, you'll be integrating this function from 0 to pi over 4 for theta and for r between 0 and 1. So now you are getting numbers only instead of functions. So technically, the one in green here should be simpler to compute than the Cartesian counterpart. Although we will not go through the proof of this formula, we can still make some sense of the formula. In the formula, we have r cosine theta and r sine theta. And that's because r cosine theta equals to x, r sine theta equals to y. That's the conversion formulas we have learned. As for r d theta, you can think of this as the dx dy counterpart. In a separate video, I will show you examples.